Thanks for your patience. We'll get started here. All right. Welcome to our second week in respirable crystalline silica exposure assessment. If you missed the first week, that's okay. Now I've been asked. I'm working on setting this up in an LMS just to sort of centralize communication and help keep people updated more easily, and also to share recordings more easily as well. I'm also going to be posting things to YouTube channel. I just haven't gotten to that. So appreciate your patience on that as well. But the previous coaching series on exposure assessment in general, or excuse me, exposure decision analysis, and then this one will be available on that. I just haven't quite gotten to that. Currently finishing up the semester with Tulane, and it's a little bit busy. So hopefully soon I'll be able to get to that. So week two, we're going to focus on sampling plan and method. So how do we actually sample for respirable crystalline silica? We don't have enough time to dive deeply into this, unfortunately, but we're gonna talk about some of the things that we need to know before we actually do the sampling on week three. So in 2 weeks, we'll discuss the actual assessment as well as uh, some of the practical tips that come from experience, I guess you could say. It is field work, it's real life, and things come up, things happen. So we'll talk about some of those issues that you might run into. But this is where we'll talk about actually collecting the sample. This will be gearing up towards that. Week four, we'll talk about what to do with our data. And then week five, we'll talk about what to do about our controls and recommendations, et cetera. So we'll cover our objectives. We'll do a quick review of the case study that we're using to sort of frame this series, and then we'll talk about some of the sampling options we have for RCS. We'll do a brief review of calibration, and then we'll also look at a chain of custody, talk about why it's important, and preview that. We'll work on filling it out before, but I just want to point out the importance of calibration and why what we're going to do with that information on the chain of custody. Then we'll review and talk about, oh, this should be week three preview. So those who participate should be able to describe two sampling options for RCS, summarize the process for calibration, and then fill out, yeah, maybe not quite fill out, but be able to explain why we do some of the things we do for the chain of custody, before and after we sample. So a quick review of our case study, and even before we get to that, just to point out where we are in that process, the exposure assessment process. We we spent most of the time in week one on these two parts, and really weeks two and three, actually weeks 2 through 4, will be focused on this number three part, and then week five on the control. So we're going to spend quite a bit of time on this third step. I guess it's justified. I don't know, but it is a very important piece. So a quick refresher on our case study. We talked about a dowel drilling company, a process that I am not familiar with. It occurs on highways, on public roads, and I'm not sure exactly what's going on there. There's either some sort of repair or installation. I'm not sure the reason for the dowel drilling, but these workers, you have a backhoe operator, and you have a what they call a drill rig operator. And you can see right there. You don't have to have any sort of special training to see that, well, there's a cloud of dust there. It gets dusty, and we need to do something about that. So we can imagine that sampling this drill rig operator, we're going to get exposures that are relatively high. We can't I can't look at that and guess where it will be compared to our PEL or TLV, but we're going to get some detection, I'm guessing, and it might be high. So these are some questions we're going to answer from the case study on the next slide. How did NIOSH evaluate respirable crystalline silica exposure? So how did they do their assessment? How did they sample? Sometimes I like to look at these NIOSH health hazard evaluations to see, to answer the question, what would NIOSH do? If I'm not sure what to do, I try and answer that question. What would NIOSH do? By looking at these health hazard evaluations freely available to anybody with an internet connection and a browser. So you can look these up and see what they did when they sampled for something. How did they approach it? And they're usually fairly detailed technical reports. Sometimes there's some information I'd like to have that they leave out, but generally good reports, detailed information, and they give quite a bit. So I am curious about the analytical method. Let's just say NIOSH Manual of Analytical Methods, NMAM. So what is the method number that they used when they sampled these dowel drilling workers? What sort of equipment did they have? Was it air sampling pumps? Did they have any size selective accessories like a cyclone, which we're going to talk about, or something else? Impactors with respirable crystalline silica, we can't just we have to make sure we select for the right size, and we'll talk about that. What was the flow rate they used? And we'll also see if we can find, and I don't remember if it's in this part of the methods, but what was the sampling time? I think we'll see that later on in a different week when we look at the results. And well, I mentioned the analytical method. So analytical method, and what is the number there? When I talk about here, this though, this part, I'm referring to, the chemistry. So, and not that if we're going to sample for this, we need to be chemistry buffs or anything. We don't have to be an expert in chemistry. It's good to know just the basic idea on how it's going to be analyzed. So we'll look at that briefly. So let's answer those questions. They say we collected air samples for RCS from the breathing zone. So that is near the worker's mouth and nose of 2 employees on 3 days. We used a 3-piece 37 millimeter cassette with 5-micron pore size and polyvinyl chloride filter. So it's a 3-piece PVC filter cassette, 37 millimeter. They used this cyclone. So I have not used that, but it's a Mesa Labs GK 2.69 high flow cyclone at a flow rate of 4.2 liters. Okay, so liters of air per minute. So that's their flow rate there. We see that they did use a cyclone. Now here they did not tell us about the pump, at least not in this section. It may be somewhere else. We don't get the pump, but we can tell we're going to need an air sampling pump. We're going to need a calibrator. We'll talk about the calibrator a little later on. And it is possible, as they did here, to use the same sample for both respirable dust and crystalline silica. So they did both, and those method numbers are 0600. That's respectively. So they actually didn't even say that there. I'm surprised. Normally they do, but that's respectively. So RCS is 7500. Respirable dust is 0600. So those are the answers basically there to most of those questions. We're going to answer a couple more in just a little bit. Their information doesn't fill in all the gaps, doesn't answer all those questions, but we know we have a cyclone. Now they're using a pretty high flow rate. that flow rate is going to dictate, or excuse me, the cyclone that you use is going to dictate what flow rate you need. Now, you may not be using a cyclone. We'll talk about impactors, but regardless, whatever equipment you're using to make sure you get respirable particles, it's going to dictate what flow rate you use. And it's very important that you use the correct flow rate. Again, we'll look at that in a little bit. We'll talk about this more next time in 2 weeks when we talk about the actual assessment in the field, what that's like. And, I mean, the whole day, we'll walk through a whole day of sampling basically. So we'll continue here. Like I said, some of those questions will be answered as we walk through the rest of this. Now, we could dive into a lot, and we're not going to, I guess, for better or worse, about respirable particles and selecting particles by size. But the point is, it's called respirable because those particles reach the alveoli, what some people would call the deep lung spaces. The alveoli is where respiration takes place. That's why they're called respirable particles, is because they reach that space where oxygen goes into the blood and CO2 comes out of the blood. That gas exchange, that's where the magic happens of the lungs. That's the functional part. Everything else is kind of like highways or halls in your house. It's not necessarily functional except for transportation, but this is where the action happens. So we're concerned about it because that is where the silica exerts its toxic effects. If it's in the airways, we're not so concerned. But if it gets down into the alveoli, then we're concerned because then we're talking about silicosis. We're talking about big problems, which we briefly talked about that last time. So ACGIH defines respirable as 4 microns, and we could get into that. We're not going to, but that's why we're concerned about respirable. And we can't just sample with any media or any setup. We have to have the right equipment to make sure that we get only respirable. You saw that NIOSH used cyclones. We're going to talk about that, but there's another common option as well that actually is my preference, tends to be a little bit easier to sample with. So let's talk about cyclones first. So they removed non-respirable particles without, well, I don't want to dive too much into the concept. It'll take too much time. I guess we could answer questions on it later if you have any questions, but we'll skip it for now. So as it says here, the flow rate is very important. We're going to look at 7500, so NIOSH method 7500, and you'll see that based on the type of cyclone, there's a specific flow rate you've got to use depending on what type of cyclone you're using. Typically for a respirable fraction, there are some that look at other things, but we're concerned about respirable, so that's what we're focused on. This is an aluminum cyclone here, and this figure on the right is, well, I'm not going to use it. It's kind of hard to read or see there, but if you envision the inside of this cyclone kind of looking like that, the air enters this little inlet right there. Maybe let me try a brighter color. That inlet right there, I've totally covered it now, but right there is the inlet where our air is from our sample is drawn in, and it will spin around and around our cyclone as it travels downward. What you don't see on this thing on the right is there's a sort of column, a central column here inside the cyclone. So it's traveling around and around that column as it moves downward, turns at the very bottom, and then travels up through that column and is going to pass through our filter where hopefully our sample is depositing, and then the air is going to continue. It's going to keep going to our pump. The main idea here is that the big particles can't make those turns. It's too sharp for them. They have too much momentum. Think of an 18-wheeler semi truck with a big load trying to make a tight turn at high speeds. It can't do it. A little sports car might be able to do it, but the truck can't do it. It has too much momentum. And so that's what happens with these particles. They hit the side, they'll fall out, they'll collect down in what this red cap on this cyclone is called the grit pot. So large particles will fall down, collect in that pot. And so this is one issue with cyclones is that you collect, actually green is not a good one on red there. You collect your grit, the large particles down here, if the worker or you accidentally invert or turn the cyclone upside down, those particles could fall through that center column and land on your filter. The problem is you don't know if that happened, but you have to treat it as if it did because again, you have no idea. And if it turns upside down, you may have contaminated your sample and you'll need to sample again. That's a challenge with cyclones. Is now there may be plenty of industries where it's not really much of an issue because your workers are not moving all over the place. But if you are in an industry where the harness is on and off, jackets or coveralls on and off, that becomes more challenging to make sure that that doesn't happen. So one thing to keep in mind, you don't want it to flip upside down. But that's the idea. We're removing the big particles, only the small collect on our filter. There are many different types. You'll see some of these listed on the NIOSH method we'll look at. We just looked at aluminum. That's most of my experience, but these are plenty common as well. So nylon or Dor Oliver cyclones, the Higgins dual, the GS1, which is used like in my experience, I've used it for diesel particulate matter, not silica or anything, but so it's often used for different things. Some of these are not for silica. There's also this one. So this is remember this is what NIOSH used. So that's that one right there. It's kind of fatter and shorter. So more of a stout profile compared to say the Dor Oliver. It's long and skinny, and the aluminum is kind of in between. The GS1 is long and skinny. It's black. It's made of non-conductive material. That's one of the special things about the GS1. Anyway, there are many different types of cyclones. That number 4 is not for silica. It's not an option for silica. So we've talked about cyclones. We'll look at how that's arranged. In 2 weeks, we'll look at what that looks like when we actually sample, what the sampling train looks like, and how everything is connected. Impactors are another option. So we could do cyclones or we could use impactors. And they use a similar idea, they just have a different design. They're going to have air enter. It's kind of hard to see there, so I'm going to draw a picture. We'll have our filter down here, and then we have this sort of plate there. What happens is, this is a simplified idea, but the air enters the impactor. It has to move around that middle section of the impactor and then come down. It comes down and flows through our filter. The large particles can't make that turn and they deposit here. Only the small particles can make that turn. And so we only get the small ones here, whereas all the large ones deposit before. So that's the main idea with an impactor. And there are many different types of these as well. So I will say I don't own stock in any of the companies that produce this equipment. I'm sharing what I'm familiar with, and that's all. There's no other reason. So this blue, if you're ever interested in sampling thoracic size, it's available, but we're focused on silica. Most of the time, I think for most scenarios, this tan, I'm not sure what they call that, but that tan colored PPI, parallel particle impactor, is the one you would probably want to use. That tan one, it runs at 2 liters per minute. This is pretty common, at least in my experience, for sampling silica. Now, that's not always the case. You may have reasons to use the orange. So this orange is intrinsically safe. If you're sampling underground in a coal mine, then you really want that to be intrinsically safe. So that would be a good option. If you are sampling a very short-term task, or if you are concerned because you believe the sample concentrations are very, very low, then you might want to use the red one here, the 8 liters per minute. That's a pretty high flow rate. And again, those are the reasons why I might use that. But most of the time, I think you're going to want to use the tan one, the 2 liters per minute one. You can see this clip. That's where it's going to clip onto the worker's collar or lapel. And this is where our hose, our tubing from our pump is going to hook up. We'll look at that more closely in 2 weeks. But that's another option. You do not have the issue of it inverting. So if this inverts, it's not a problem. Nothing, no contamination. We're still good. That's one thing I like about it. In my experience, it's also easier to calibrate. That's just my experience. But after having experienced using these, it's my preference. They tend to be more expensive than the other option. So these will cost money, whereas a cyclone you can reuse. You can keep reusing it and just buy it once, whereas each time you sample with these, you'll have to pay the lab to use it. Uh, to me, it's worth it. I've just started to use them all the time. So here is that sampling method I had mentioned. This is 7,500. It is for crystalline silica. So this is for respirable. It doesn't say that, but it's for respirable. We can see that the analytical method here is XRD, X-ray powder diffraction. Not that we're going to talk about how that works. To be honest, I'm not totally sure how that works. We don't need to know how it works, but it's good to just make a mental note of the method for analysis. There's a lot of information here. If you've never seen one of these, it can be sort of overwhelming. Um, so, like I mentioned, I'm planning on populating an LMS, so an actual sort of class structure to these. It'll still be free and everything. Just it'll be more organized, and I'll share a document I have that's a sort of guide on how to read these. What is all of this information? I did not put the guide together. Someone else did, and to be honest, I'm not sure if they even put their info on there. So, good for them. But anyway, they put this guide together, and it can be very helpful if you have never seen it. You can see some regulatory exposure limits here, and just guidelines, ACGIH, for example. So, most of the information I refer to is in this left section of the method. I do often I may sometimes look at this right here, the limit of detection, and somewhere else the limit of quantification. We're not going to dive into that today, but those are sometimes things that I pay attention to. We're not going to look at it today. I just don't have enough time. So the sampler tells us, okay, if we're using this method, it's a cyclone. Now, the PPIs, parallel particle impactors, they use the same. It's a modified version of this same method. It's essentially the same, but you're going to use the flow rate that the PPI says. So if it says 2 liters per minute, you're going to use 2 liters per minute for your flow rate. We can see here that the flow rate is dictated to us. So if we have a nylon cyclone, it's going to be 1.7. We have the The HD, I know dual is the second part. I'm forgetting the first part, the H, but it's 2.2. And if we're using the aluminum cyclone, it's 2.5 liters per minute. So we need to make sure that we match what our cyclone is, its type, to the flow rate NIOSH says to use. I will say, again, we don't have time to dive into this. I do like to pay attention to the volume range. The lab, my experience, and I could be wrong, but my interactions with the lab have led me to the conclusion that it's not just lab, actually. NIOSH says this in the manual, in their manual for the analytical methods. These are sort of recommendations. The flow rates, I would say, you really need to match the flow rate. You've got to match the flow rate. These volume ranges are more of a guideline or recommendation. The lower range is to try and help you get detection. So they recommend at least 400 liters to ensure you actually get a quantifiable sample. The max for 1,000, that is to prevent overloading. Again, so I would use those as more of guidelines. If I am outside of that range, I'm not super concerned if if I can't be. I'd like to be in that range, but if I can't be, I'm not too stressed about it. Sometimes I've been much higher than a 12-hour shift at 2.5 liters per minute if I'm using an aluminum cyclone. Let's see, 12 hours is, let's do the math here real quick. That's 720 minutes times 2.5 liters per minute. I'm going to be at 1,800 liters. So if I sample the whole shift, I'm at 1,800 liters. I'm well above the range. I'm not too concerned, even in a mine, of overloading. Now, overloading could happen in a mine, but most of the time it's not going to happen. So anyway, that's just an example. It'll tell us about the shipment. So nothing special with RCS, thankfully. It's pretty stable. You should read this, but for RCS, there's nothing of note here. Things are easy. Uh, NIOSH recommends 2 blanks per set. We'll talk about blanks next time in 2 weeks, but I normally do 1 for every 10 samples. That's what I was taught. That's what most people I know were taught is 1 for every 10. NIOSH recommends 2. Uh, it's kind of, it's good. You have to pay for those blanks too. So anyway, most people I know just do 1 for every 10. And that's it for this. Most of the information I'm going to use is here. I don't have it, but on the second page, page 2, it does talk a little bit about the sampling setup itself. So you may want to refer to that. We're going to next week or in 2 weeks, we're going to go over that. So I'm not going to go over it right now. I want to talk more about the method and kind of getting ready to actually sample. So that's about it for the method. And I wanted to do a quick review of calibration. I think calibration, it probably deserves a full hour or more. And there's just too much. And so I want to do just a quick review for calibration. Maybe I'll do a whole series on calibration. I don't know. But anyway, so we'll just do a quick review of what that's going to look like. And I want to just say briefly that we put a lot of effort into getting our sample. We pay a lot of money and we spend a lot of time getting our sample. But at the end of the day, whatever number the lab gives us is what I would call a surrogate for reality. We cannot know exactly what our workers' exposure was. We will not know exactly what they were exposed to. We try to get as close, as accurate as possible with our sample by sampling in the breathing zone, using the correct flow rate, using the proper setup, by calibrating, by using blanks. All of these things that we do, they are ways for us to quality control ourselves. There are ways for us to reduce what I would call uncertainty associated with the process. No process is perfect. No process will be error free. So the goal is to reduce it as much as possible. So everything we do is to reduce uncertainty and be as accurate as possible, as humanly possible. But I just like to keep in mind that at the end of the day, the number we get is still, it's not going to be exactly what our worker was exposed to. Hopefully it's close. So with calibration, that's one reason we do that. We want to be accurate. We don't want to over or underestimate the actual exposure. We want to be as close as possible. There are different types of calibrators we use. This is kind of a wall of text. I'm not going to read all of that, but basically we have primary standards and secondary ones. There's intermediate. I'm not going to really talk about those, but a secondary would be for the field. We'll take a look at some of these. The primary is what we're going to use to actually calibrate, meaning we're going to set our pump to the calibrator, whereas secondary, we're just doing a quick check to make sure we're about where we think we should be. So these are some examples of primary calibrators. You have a frictionless piston calibrator. This is what I use most often. Not this exactly. Again, I don't own stock in any of these companies. They're just pictures. And, I've used each of these things and I've used other things. Anyway, you have a bubble, the soap bubble meter. That is a primary standard. I don't see that used very often. Now this one, to be honest, I'm trying to remember if the Checkmate is a frictionless piston calibrator. I don't remember, but it's easy to use, and it's fairly common. So these are the types of calibrators we would set our pump to. Oh, let's see if we got a mass flow meter. Thank you, John. Thank you, John. Yeah, it didn't seem like there would be, so I should probably add that to this slide here, mass flow. Whoops, mass flow. So I'll have to make a note and add that here. Well, let's see. I guess we got film flow. No, mass flow. So we can set our pump to any of these things, and we should feel pretty confident, assuming we've done it properly. Secondary would be a rotometer. So you can't see it. I should have gotten a side view, but on the back side of this would be two nozzles, and one would be, let's see, we'd hook up our pump to this part. It's going to be drawing air through that and push this steel bead up. And that's a pretty high flow, to be honest. That's 10, 20, 40 liters per minute. I'm not usually dealing with flows that high, but as it says, this is just for a quick check in the field to make sure we're in the ballpark. And you know what? We'll talk about why calibration is important, but I'm not going to be able to dive real deeply into how we do it. So I think we'll kind of preview it today. And in 2 weeks, we'll talk about calibration and the sampling. It's our sampling day, so to speak. We'll talk about both and the how-tos for those. So when we calibrate, there are a few things we need. We need our calibrator. We need some Tygon tubing. So that's the tubing you see here. We need our sampling pump. So when it says, oh, actually, we're not there yet. So this is, and I don't have a picture for respirable crystalline silica, but you know what? I think I did. I took one of my own pictures out. So let me see if I. Oh wait. Okay. We do have. So we'll look at that there. Forgot I had that still. So we'll need calibration media, meaning we should have in the case of silica, we should have either a PVC filter cassette or a PPI that we use for calibration purposes. I've heard of people who have a different approach. This is the approach I learned and the approach I use. And then I write on that cassette or that PPI calibration or cal so that I know I'm using this for calibration. There will be, let's say you have post sampling at the end of a shift when you've sampled. Maybe you will have a lot of loading on your sample that was out in the field. And so the resistance will be different compared to your calibration media. However, and so I've heard some people say that they use the sample for post calibration. It's probably not going to get contaminated, but I did not learn to do it that way. I still use my calibration media for the pre and the post check. Excuse me. So so we'll want a piece of media that we can use for calibration. And there may be, so this says equipment. We're going to look at some of that equipment. Now this is we're not going to use that for RCS, but with a cyclone, we will either need an adapter or a calibration jar. And with a PPI, it's the same idea. We're going to need a special adapter or a calibration jar to do our calibration. So let's look at those real quickly. So this is the type of adapter that would go on our PPI. It has a little, you can't see it, but there's an O-ring inside here that creates a seal. So we set it down on there and that O-ring fits nice and snug right there. The idea is this, there's going to be a tube here that goes to our calibrator and a tube here that goes to our pump. We need to create a seal around here where the air comes into the impactor. So that's what that adapter does. I'll talk about the adapters, then we'll talk about the calibration jar. So for the Cyclone, some of them have special adapters. This aluminum one has an adapter, so this would go up and over, and you can kind of see it there. It has an O-ring inside there. That O-ring is going to fit nice and snug right there to create a seal. And it's the same idea again. So the PVC filter cassette on top of that is going to go to our pump, and the adapter. So it's always the adapter goes to our calibrator, and our media, our filter, our sampling media, or let's say calibration media, is going to the pump. So just like when we sample, our media goes to the pump. Well, when we calibrate, media is connected to the pump, adapter connected to the calibrator. In the jar, it's creating that seal, but just in a different way. We don't have a special adapter. We are going to attach, so if it's the PPI, we attach the PPI, the clip would hang down there. We attach the PPI on there. It's not the most elegant setup, but it works. Or you set up your filter cassette. So you'd have your cassette with your Cyclone on it, and the inlet right there, that would get attached to this center tubing. So just like when we sample and just like when we use the adapter, the piece that's connected to the media, this goes to the pump. And this is going to have tubing that goes to the calibrator. So this is an example. And now, like I said, we're not going to dive into the how-to today because I'm already over time, and I don't have the picture that's specific for RCS today. But you can see our media is connected to the pump. Now there's no adapter here, but if we had an adapter, then that's connected to our calibrator. And again, we'll talk more about that in 2 weeks. I talk too much. And I think we'll go over this procedure as well. So we talked about kind of the idea and some of the specifics. We'll get into the procedure next time, as well as the sampling and what we do in the field, for example. Yeah, so we will cover these details next time. So I've been talking a lot. I'm gonna turn this to you a little bit. So why is a chain of custody important? When we're done, we're going to fill out a chain of custody. We're going to send it off to the lab. There are a few reasons why it's important. Some of it pertains to sampling itself. Some of it is for liability purposes. I guess we'll talk about both, but I'm curious, but we'll talk about one more here. So why would a chain of custody be important? John says establish air volume collected for each sample. Perfect. Good. We and so let's get the liability one out of the way first. So it is for liability purposes. It's to show that so for example, if your sample is involved uh in in a lawsuit, let's say, a worker was overexposed, they have an occupational illness, and there are attorneys involved, and they're paying close attention to every sample that ever has been taken and will be taken, is currently taken. It demonstrates a chain of custody to show who possessed the samples and hopefully to ensure that there was no tampering with samples. So that's the liability one. It's important. We're not going to focus on that. Let's talk about the volume. So the remember concentration is a mass per volume. We'll talk about this a little bit more later, but the lab is going to measure the mass. They're $1 million pieces of equipment. It's more than $1 million, but multi-million-dollar pieces of equipment are going to tell us what the mass is. So they give us that number. We have to give them this number, the volume. And we ran out of time today, so we'll talk more about that. But this is part of we'll talk about how the flow rate ties in, but it's why it's very important that we make sure we get the flow rate, make sure we document properly and get the sampling time. Both of those things are going to help us get the sample volume. So we give the lab the volume. The IH is going to give the volume. The lab is going to give the mass. And because they have both numbers, they calculate that for us. It's very nice of them. I mean, we pay them enough that they could just run that math for us real quick and give us a concentration. So that's those are two big reasons why chain of custody is important. We won't. I do use Galson. I'm not promoting them. It's just what I have, but we'll talk about this more next time. Uh, again, I'm running over time, so quick review. We reviewed our case study of the Dow drillers. We looked at how NIOSH did this. So they used 7,500, but they used the GK 2.69 cyclones. We looked at some different sampling options. So you can use a cyclone. There are pros and cons to each of these, and then the PPIs, parallel particle impactors. We did a quick review of calibration. We'll dive into that more deeply next time. We did a quick review of why a chain of custody is important. And I wish we had time to, dive into some more things here. Particle size distributions and things that there's just not time. And so anyway, I want to use the last 10 minutes or so here to answer questions. So while I wait to see if there are any, I'm going to let's do a quick preview of next week. So next week is our sampling day. We'll, we're going to virtually go into the field and sample our dowel drillers. We'll, like I said, because I did not quite get there, we'll talk about calibration. So if you're familiar with sampling, you know that I'm thinking of, say, I don't know what kind of shift, I don't remember what kind of shift these workers work, but your day starts early because you need to calibrate that morning. Oh, we got a couple of questions. Let me finish my thought here, and then we'll get to these comments and questions. Your day starts early, so we'll talk about the how-tos of calibration. How do you do that? And then we'll talk about the actual sampling in the field. What kind of notes should you collect? What kind of information should you gather? How often should you be there? Do you hover over the shoulder of the worker, or do how do you do that? You don't hover. You can probably guess, but just what does that look like? And then on the post side of things, so after you're done sampling, what do you do? So we'll talk about that. Week 4 will be once you get your data back, how do you analyze? And week 5 will be, okay, what the so what? So what are we going to do about these results? So let's take a look at these comments here. Jimmy, did you say something at the beginning about having these sessions uploaded? Jimmy, yeah, I'm going to I I created an I created a free Canvas account. I'm familiar with Canvas because of through Tulane and U of A and the universities I've taught. So I'm going to use it just as it's more of a central place. It will help with just centralizing resources and the recordings and announcements and and the Zoom links, calendar invites, etc. So I'm going to use that for that purpose. I also plan to, I've created the YouTube channel. I just haven't processed all the videos and uploaded them, but I do plan to put them there. Again, all of it free. I do plan to have that. I just am slow right now, working on that, but it will be coming soon. I should have a little bit more time soon. Would like to know what type of personal pump can be used with cyclones flowing in excess of 4 liters per minute. That's a great question. So John, how much greater than 4 are we talking about? I mean, is this 5 or is this 10, 15?
Oh, there was one cyclone that I think in an earlier slide, and I thought it looked like it was using 8 liters a minute or so. Was it the BGI maybe?
That was the PPI. You're right though. Right there. So
Well,
you're right.
but there was another impact. Besides the impactors, there was a cyclone. Oh, it doesn't specify flow rate. Okay.
Well, but NIOSH was using 4.2
Yeah.
with their GK
Really.
2.69. So my I have not sampled at 8 liters per minute with a personal sampling pump. So I'll be honest, I don't know how to answer your question exactly. I think most are good up to 5. They should
Right.
be, most are good up to around 5. Um, I might be wrong, but most of the common, top of the line pumps will do that. At 8, I really don't know. I'll have to dig to answer your question, but I think most should be able to handle 5.
Do you know if I could interject? Yeah, I have a client that it's a power client. They service transmission lines, etc. And I periodically do exposure monitoring for them when they're wet sawing concrete poles. And, in 15 minutes, they can saw 4 or 5 poles. So how long are you going to sample for 2 hours? So yeah, I was looking at those 8 liter a minute PPIs, was wondering if anybody knew of a sampling pump that would support that kind of flow rate.
Yeah, so if anyone knows, feel free to put that in the chat or to chime in. That's if I remember, I'll look into that. But hopefully we can get an answer by in 2 weeks. And then a little bit related, Edu, sorry if I'm saying your name wrong, says, why would you use a flow rate of 4.2? That's a great question. So I'm going to go, sorry, I'm jumping here, but I'm going to jump to our, so, well, you know what? So this method does not specify for the GK. So the GKs that NIOSH uses that must be the flow rate that they require. NIOSH has their own analytical lab, so they may have more flexibility than you or I would. We have to do what the lab and the methods say. They have their own setup, and they may, I don't know, but I suspect that GK just that's what it requires is 4.2. Good questions here. In the work shift in an industry is officially 8 hours, but different employees sampled worked different extra hours. Would you use the brief and scala to estimate the TLV per employee sampled? MG, great question. And yes, yes. So that would be the best practice. Not everybody does that, but I would recommend that. You can always, my thought is you can always compare to both, right? You could compare to the regular 8 hour TWA, but also adjust your TLV or PEL per brief and scala to show what it ought to be. My experience is also that unfortunately, those workers who work the long shifts tend to also be at greater risk of overexposure. That's my own, my background is mining. So maybe it's different in other industries, but that is generally my experience. Is those are the workers who, they're the ones who do the real work, let's say, the hard, heavy lifting for the operation, and they get exposed more, more frequently in my experience. Anyway, so that can be a challenge. In an industry with very low silica concentrations, where you use a high flow. Great question, and that's something that as we're talking, I'm considering. In mining, again, my background is mostly mining. It's usually not difficult to get detection, but over time, as we get better, I mean, it's a good thing, right? We're getting better, uh, on average at controlling exposures, and it may become harder and harder to get detection. And so there may be more of a shift towards the 8 liters per minute, whether it's a short task or just concentrations are very low. And so we could ramp up our flow rate to get a detectable sample. So it's something I would definitely consider. I'm considering it right now. I just got to do some research on what sort of pump can do 8 liters per minute. So yeah, those are all great questions. Wow, really good questions. Any other questions? Cool. Well, thank you. I do not communicate about this as much as I should. But if you filled out the registration link, then I believe you can get a calendar event to help you remember. But we will do it again in 2 weeks at 4 p.m. Pacific or 7 p.m. Eastern. And like I said, I am working on that the YouTube channel and an LMS or something. I need something to sort of centralize. LinkedIn is not meant for that. Um, so I'm working on that, and it should be available soon. But I appreciate everybody for coming, and hope you have a great 2 weeks.
Thank you.
Yeah, you're welcome.